Naimbag nga aldaw, mabuhay. I'm here to present to the first international conference on technologies for smart green connected society 2021. Our research titled Chlorophyll-A pigment measurements of Chlamydomonas REINHARTTI using portable pulse LED LIDAR system. I'm Mr. Jumar G. Cadondon together with Doctors Edgar A. Vallar, Emelina H. Mandia, Tatsuo Shina, and Maria Cecilia D. Galvez. We aim to design a portable pulse LED LiDAR system for algal growth monitoring. Why do we need to design or to create a LiDAR system? We experience that most of these standard methods and requires water sampling and it's tedious, which does not provide real-time monitoring. With this developed LiDAR system, we aim to um, advance in the development for a real-time monitoring in algal growth. The flow of the presentation starts with the motivation and background of the study, the objectives and methodology, data and results, conclusion and feature works, and appendices. As we all know, algae could conduct photosynthesis, which on their own they produce their nourishments. There are different uses of algae for commercial uses such as for biofuel, bioplastics, animal feeds and fertilizers, foods, and others. However, there are several factors that we have to consider for algal growth. First is light, which is both duration and intensity, nutrients, temperature, pH, and salinity. Changing one of the factors may cause what we call an algal bloom, which causes illnesses which are associated to these harmful algal blooms. 2 of the 17 United Nations Sustainable Development Goals was targeted, which is first in clean water and sanitation. In the Philippines, it's about 20,200 mcm groundwater is in demand, wherein also due to the changing climate, we targeted goal 13, which is climate action. These are the objectives of the study: to construct the transmitting and receiving systems of the pulse LED LiDAR system, and to measure the fluorescence, the chlorophyll-A fluorescence echo signal of the algal growth at laboratory cultivation parameters. And lastly, to correlate this measurement to the standard methods which will be presented later on. As we all know, there's a significant specific optical properties of algal samples, which on the relative intensity, they vary based on blue-green algae, and diatom. However, almost all algae consist of a particular component or pigment, which is the chlorophyll-A. We plan to use a remote sensing method, which is non-invasive, to detect the fluorescence of atoms and molecules in algae, specifically for chlorophyll-A. Most of the LED LiDAR systems are used for atmospheric applications and lately for Mars rover applications. With its portability and ability to conduct real-time monitoring at a cheap budget, we aim to design a different LED LiDAR system which focus on coastal monitoring. According to these researches, there are several growth dynamics of algae from exponential growth, stationary to the decline phase, and we aim to show this using the LiDAR signal from the developed pulse LED LiDAR. How does our pulse LED fluorescence LiDAR work? So the design of the LiDAR is divided into the transmitting and receiving systems of the LiDAR, which is a biaxial system, and we measure the initial optical parameters and used it to measure the fluorescence echo signal from the Chlamydomonas. So this is the actual tank used for monitoring, and this is a schematic diagram of the system. This is the actual setup. The centimeter should be in inches, and as you notice, The LED LiDAR system consists of a PMT voltage source and an LED source and a monitor to determine the signal coming from the algae. So the transmitting system of the LiDAR system consists of a 385 LED wave, LED Nichia brand, and this is the pulse frequency circuit. This is the trigger input, and this is the LED transmission system, which we measured with its approximately 385 nanometers plus or minus, and the pulse width at 10.92 nanoseconds. The receiving system is a revised Smith-Cassegrain telescope with an optical filter of 680 for the fluorescence emission and a detector of a photomultiplier tube, and for the photon counting, an FPGA-based photon counter board was used. This is an example of a data acquisition conducted for the LiDAR system. For the alignment, we have measured that the beam diameter is 50 and the beam divergence of the transmitting LED is 5. And for the receiving system, which is the telescope, its beam diameter is 100 and beam divergence of 3. We also prepared the inoculum for the algae, which is at 12.5% inoculum with an initial optical density of 0.3. We have replicated them into 3, and this is the culture media used, which has a specific components of nitrates and phosphates necessary for the algal growth of the algae. The photo period is 12 hours light and 12 hours dark to mimic the light-dark conditions in the system. To further identify some of the factors that may affect the algal growth, we have installed a weather station that measures the humidity and the temperature, air temperature, and the pH and water temperature sensors were also connected together with a tank that controls the aeration and the oxygen level in the water. For the LiDAR system, we have initially measured the background noise with 3 different types of signals. First is the culture media without the algal sample. The second one is using by covering the pulse LED or the transmitting system, and the third one is by covering the receiving system. The standard measurements used are the absorbance spectroscopy and or the optical density measurements, and the second one is the fluorescence measurements. This is an example of a fluorescence measurement collected from the spectroscopy setup, and this is the excitation wavelength, and this is the algal organic matter component, and this is the pigment component of the algae. From here, these are the noise measurements conducted. Notice that there's no significant differences between the 3 noise signals that were measured, and this is the fluorescence echo LiDAR signal with the corrected and uncorrected data. On the other hand, this is the range resolved fluorescence LiDAR signal of the CHLAMYDOMONAS SP at the initial conditions. This is the algal organic matter, which shows you the growth of the algae from the lag phase or the initial phase to the exponential phase to the stationary phase and the death phase of the algae. Notice that at day 13, the death of the algae was shown. However, for the correlation with the fluorescence LiDAR signal, we opted only days 1, 5, and 10 to present the lag phase, the exponential phase, and the stationary phase growth of the algae. These are the optical density and fluorescence EM measurements, which are considered to be the standard methods of measurement. As you notice, as the days increases, the optical density increases, same with the chlorophyll-A signal, and hoping that this also shows with the fluorescence LiDAR signal. Now, this is the range resolved fluorescence LiDAR signal of all 3 days, from day 1, day 5, and day 10. And as you notice, as the day increases, or progresses, the fluorescence LIDAR signal increases as well. This shows high correlation of values, and at day 13, notice that the relative temperature and humidity increases, which cause the death of the algae. In conclusion, the transmitting system of the pulse LED LiDAR at 385 excitation wavelength is a bandwidth of 10.42 with a repetition frequency of 475 kHz with the maximum power of 830 milliwatts. For the receiving system, it's only at 680 for the Chlamydomonas sp, and showed positive correlation for the chlorophyll-A pigment and the optical density measurements together with the fluorescence measurements. There are other components that were also measured from the organic matter component, which showed high correlation as well, such as tryptophan-like or the protein-like signature and the humic acid components of the organic matter. The developed LED fluorescence LiDAR system was found to be useful and showed high correlation in estimating, and the variance in the chlorophyll-A concentration can be attributed to algal organic matter and some physical parameters such as light, temperature, and humidity. In future, we plan to automate the LiDAR system and to provide a seasonal algal growth monitoring using the LiDAR system. We would like to acknowledge our project Water Quality and Fluorescence Measurements of Water Bodies for the funding, and UP Visayas and ASTHRD for the scholarship. References. Thank you so much for watching. It's more fun in the Philippines.